right, so I'll be continuing with what Terahisa talked about. In particular, I want to say something about how to prove results from the first talk. And what are some of these results, just as a reminder? So Terahisa defined some L cusp, and this should be the same thing as R cusp. There's also cusp is generated by these cuspidal vector bundles. Just a reminder, there will be some vector bundle on the Vogel variety v lambda, and this, okay, it begins. Okay, and this, how do we get out of it? Okay. Oh, do you know why it's doing a text box? Oh, I just clicked that. Okay. So this, there's an inclusion like this, and then the cuspidal vector bundle is just, let's say there's some V rho, and it's just like I phi lower star of V rho. Okay. And then this category of cusp is semi-simple. And there's a classification of these cuspidal, the simple objects are these cuspidal vector bundles, and there's a classification of these. And then finally, there's this semi-orthogonal decomposition of par G that Terahisa mentioned. Okay, so I have to do next page or something? Okay, swipe more aggressively. Okay, great. So the point of the last talk is that we're interested in these questions on par G, and actually there is some big reduction that we do to actually trying to prove these questions on the cotangent stack. So maybe some people were asking in the break, like, how exactly does this reduction work? So we can talk about that later. And the question is like, yeah, so what I want to talk about is once we're in the cotangent stack setting, how do we prove some of these things? Okay, so K prime, so characteristic of K bar is 0. So we're taking some algebraically closed field of characteristic 0, and we're working with G over K bar reductive. And as Terahisa mentioned, there's going to be some co-character in some maximal, co-character in the maximal torus, in some fixed maximal torus of G, and that is kind of like what's left of our parameter after we've done all these reductions. And this is going to give us some space V lambda, which is, or just V, which is exactly the n-graded piece of the Lie algebra. By the way, another comment, I'm writing G everywhere, but this, you should think everything is happening on the spectral side. I'm just omitting all the hats. Okay, so this V is just the n-graded piece of the Lie algebra, and this H is just the centralizer in G of lambda. Okay, and then this Vogel stack in this case is just V mod H. And, all right, and so what we will be considering is, we will be considering this cotangent stack. I'll probably forget to write the little star there many times. And since we haven't really seen any examples of this, I'll give you one example. So I want G to be SL2, and I want lambda to be this thing. And I want, so in this case, V will be just an A1, and H will be a GM. It's not for, there's like maybe a minimal choice, but you know, it could be, like if n works, 2n will also work, but you would then change your co-character. Yeah.
What is the relationship between lambda and n at all?
So lambda gives you an action of GM on the Lie algebra, and then we're taking the weight n piece. right? Characters of GM are famously integers. Okay.
So for this sense, you just said if you replace lambda by n times lambda, then you can just assume n is small.
No, you can't go, there's a limit to how small you can go. Yeah, but you can make it bigger if you want. Okay, so what does this cotangent stack look like in this case? So it lives in, you can think of it as living inside of, so you can think of GM acting on this picture that lives inside of A2. And so it's like the quotient of this by GM. Dave, are you okay? Okay. N in this case is 2. N equals 2. And there's, in fact, 3 orbits in this case. So I want to make a statement here. This is not the cross that appeared several times in earlier talks. This is different. Okay? So but it's going to look a bit similar because, in fact, this Vogin stack is lying in the horizontal component. And this thing also showed up in the cross. This point, there's three orbits of this thing. Okay? This is the cotangent I'm drawing. Okay. And then there's phi triv, and that's this point here. And then finally, there's a vertical orbit that I'll write psi triv. Because you should think of this vertical orbit as corresponding to the Arthur parameter of the trivial representation. So these Arthur parameters that haven't really featured much in this conference actually show up in this setting.
What is this a picture of?
This is a picture of, so the cotangent stack is some, at least the classical part, is some variety, in this case in A squared, and it has an action of GM, and then we're taking the quotient.
So this is like A2 modulo an action of GM?
Yeah, but it's not all of A2, it's just the cross.
So it's not an A2.
It's in A2.
It's in A2.
Yeah.
And projects to V, right?
So TV, so the classical part of T star V lives inside of V dual mod H. So that's why I'm trying to say that it lives in A2. Okay. All right. So my idea is that I have 3 vignettes about different things we can do with these cotangent stacks, and these will lead us to figure out different proofs. And I probably will not get through all 3, but that's okay.
Sorry, what do you mean by classical part?
Right, so this T star V is almost always a derived stack. So like so unlike par G, right? So you might think, well, why the hell are you doing this? Well, firstly, we always have to deal with derived structure anyway. Par P can be derived. And secondly, the derived structure here is very mild. So it's best to just like hold your nose and deal with it. And another thing is that this derived structure is actually kind of essential. If you deal with just the classical stack, you'll see that all these results are wrong. So there's maybe no way to avoid it. So
Do you mind scrolling up a little bit so we can see the previous page? Just some part of it.
now I'm in another talk. Wait, hold on. Okay. Eisenstein series on T star V. So this is the first thing. And so the first thing that is very important for us is a definition. So theta is defined to be A1 mod GM, where GM is acting by weight 1. So why might I do this? Well, I can consider this mapping stack like this. And you should think of this as some stack of filtered points of the cotangent. So this A1 mod GM has 2 points, right? It has a closed point and an open point. And so the closed, yeah, so, okay, anyway, there's this Rees construction. Like, this is kind of a pretty classical thing. So this mapping stack is a stack of filtered points. And one proposition that I'm going to attribute to Halpern-Leissner but maybe is kind of not so hard to see, is that this mapping stack actually is isomorphic to a disjoint union of co-characters nu. Take the Weyl orbit, and then, okay. So this is just notation, but what I should say is that these stacks are actually not so complicated. The idea is that you take your co-character nu, you find a representative DG algebra for the cotangent stack, and you just take like the nu greater than or equal to part of that DG algebra. It kind of acts on the whole picture. So this T star V, nu greater than or equal to 0, is going to be isomorphic to like spec A mod P nu, where A is, okay, maybe the parentheses are, so A is like some DG algebra, and P nu is like the parabolic associated to nu inside G.
I'm sorry, theta is A1 mod GM. Why? Where did it come from?
Right, so this may sound very unmotivated, but if you'll give me 5 minutes, it will sound more motivated. Okay.
In the case of the previous example, is it easy to say what this looks like?
Yeah, we're going to get there. All right. So I want to make another point, but let me not write things since I'm getting stopped a lot, is that like you can also consider this mapping stack for the classifying stack of GM, and then you will get some kind of graded points. And there should be, okay, so let me not get ahead of myself. So the key diagram that we're going to get is as follows. So, and hopefully this will start to make Jared happier. So this nu equals 0 is the associated object for the graded, for when you replace theta with the classifying stack of GM. And this thing is some quotient by like the Levy. It's like some G algebra mod the Levy. So we have some map P like this, given by evaluation at the open orbit. And we have some of theta. We have some map like this, given by evaluation at the closed orbit. Let's call this Q. And then we also have some map sigma, which is like including the close point. Okay, so this is starting to look a bit like these Eisenstein series diagrams that we've written a million times so far in this conference. So what is the proposition? So the proposition is that star is the Eis diagram for lambda and P nu. So what I mean is, so there is some Eisenstein series diagram for par G. And so Terahisa was describing how we can reduce to this completed fiber and then pass through some Koszul duality to get to this cotangent stack. So what you can do is you can take the whole Eisenstein series diagram and you can pass it through all those equivalences. And the claim is that the diagram you end up with is this. And there's some like non-trivial thing to check here because what happens when you pass through Koszul duality is that each map becomes a correspondence. So there's actually a composition of correspondences, and this middle object turns out to be this thing. Okay, and so the Eisenstein series so I'm going to write cotangent here for one time, but I will not in the future, is given by P lower star, Q upper star, tensor with omega v mu, or vu. So omega vu is some kind of relative, well, okay. It is this. So you can take the Vogel stack for the parabolic, the Vogel stack for the Levy. Each of these have dualizing sheaves, and it's the tensor product of they turn out to be line bundles, and it's the tensor product of one of them with the inverse of the other. So I'm denoting it VU, so it's kind of like the Vogel stack for the unipotent radical.
What sheaf category are we doing this in?
Yeah, I guess like coherent sheaves on the cotangent. Maybe there's, yeah, some statement about things being quasi-smooth and maps existing, but anyway. Right, and but a natural question here is what the hell is this dualizing sheaf? Well, this comes from this equivalence, right? When at some point some map turns into a correspondence and there's an upper shriek and you want to turn it into a star, and so then you get this dualizing sheaf. So, okay.
Sorry, what's the subscript for this?
For what?
If there are, so the subscript.
P nu is the parabolic, M nu is the levy, V is the Vogel stack.
And what is new?
What is what?
What is new?
Nu is the co-character that shows up in this decomposition of the mapping stack. So the point is every co-character shows up in this decomposition. So if you want to compute some Eisenstein series, really you can just like look inside these mapping stacks. Okay. So now let's assume G is semi-simple. This is not necessary, but it will simplify things a lot. Okay, I didn't need to assume that just yet, but let's keep going. Okay, so what is an advantage of thinking about these mapping stacks? Why are we doing all of this? Well, the work of Halpern and Leisner tells us that so there's a theta action on T V nu greater than or equal to 0. So the point is this is actually some connected component of the mapping stack. And this theta is like some monoidal object in the category of Noetherian-derived stacks. And it acts on the mapping stack by like precomposition. And so one thing you realize is that this TV nu greater than or equals 0 carries an action by this theta. And this induces what Halpern and Leisner calls a baric structure. On co T star nu greater than or equal to 0, and also on the nu equals 0 stack. Okay, so what is a baric structure? It's a family of semi-orthogonal decompositions like this.
Is that say?
SODs,
No, after the first angly bracket, what does it say?
co.
Oh.
Okay. So some family of semi-orthogonal decompositions, and you should think of this as giving some kind of weight decomposition of the category, but it's not an orthogonal decomposition. Although on the levy, it actually turns out to become an orthogonal decomposition, and also it's compatible with these central weights that have shown up a number of times. I'm just not rewriting the whole thing over again. It's T star V, it's the cotangent of nu greater than or equal to 0, right?
What's this index, W?
This index, okay, yeah, fine. So W is in Z. Yeah, good.
Here's a naive question. Theta is not a group, right?
It's a monoidal object. There's a tensor product. It's a monoidal stack, Jared. You can take nu equals 0, but it will not be interesting, right? Okay. So, okay, the first proposition that maybe is some indication that this kind of thing could be useful is the following. So if F is a coherent sheaf, then F is in R cusp, respectively in L cusp. Let me try to squeeze it on this page. If and only if P upper shriek, F is in here. So, okay, so let me just say, like, so this is the R-cusp version, and I've run out of space to write the L-cusp version, but it says that the Schrieg pullback of F to this stack is of weight less than nu paired with the total weight of this line bundle. That's the thing that you can make sense of. Okay. And a similar thing is true for L-cusp, but in this case, you take P upper star of F, and it's greater than weight nu with the same, it's like greater than the same thing. Okay.
And this is quantified for all nu?
And this is, yeah, for all, if it's in L-cusp, if for all nu. Right, exactly. We need to look at all parabolics. Okay, so one corollary of this is that L-cusp is the same thing as R-cusp, actually, on the cotangent stack. So why is this true? So there's a diagram like this. P, let's call this P op, Q op, Q, and then there's also maps sigma and sigma op. Okay, and this diagram commutes. Okay, and so now, like, how does the proof work? Well, first of all, we want to use this proposition, and so we say that F is right cuspidal if the Schrieg pullback to TV has a certain weight, but then these baric structures have a functoriality. So in fact, we can measure that weight on TV nu equals 0, pulling back further by sigma. Okay? But now the diagram commutes. So that's like pulling back all the way on the ops. And then you relate this weight condition on the nu thing to the weight condition on the nu op, or the negative nu thing, and you end up just getting that this thing is in.
Maybe one comment, P is quasi-smooth.
Yeah, P is quasi-smooth, so these Schrieg pullbacks are. Yeah. Right, so this is already surprising. This is actually something that we had a lot of trouble proving in other ways, but it just becomes pretty easy here. Another thing is that, so this is not an obvious consequence. So the setup is that F is a coherent sheaf on some levy with weight, and this is like central weight corresponding to the Kottwitz map of BM, where BM is basic in G. And in this case, I's P nu of F is a basic sheaf. And this is not obvious. But it roughly, the proof requires some version of this like spectral geometric lemma that showed up in Lucas's talk. But let me just point out that we're in an easier case here. For starters, we have this baric structure. And for seconds, this cotangent stack has a much simpler geometry. So you can imagine that something like this can be dealt with.
So is F assumed to be cuspidal?
Sorry, F has to be basic. Thank you. And let me just say that actually to prove this basicness, right, we're proving that that if you map any like Eisenstein series into this F that has some dominance condition, then you get some vanishing. So we're really showing some vanishing of some R-HOMs. And let me just claim to you that like a souping up of this argument will lead to this semi-orthogonal decomposition. I didn't plan to say a lot about that. Okay. So this is the first thing. The second thing I wanted to talk about is cuspidal sheaves and exceptional extensions. So something that Terahisa mentioned is that cuspidal constructible sheaves are IC extensions from open orbit of V. And we kind of want something like this in the coherent setting. So what? Clean. I mean, what I wrote was correct, but the cleanness is critical. So clean means the shriek equals the star. Now, you might think like you could try to pass through these filtered D modules that showed up in the previous talk, but it turns out that that's actually, right, it's more like a correspondence of functors, and that's actually quite tricky to deal with. So that's like not what we're going to do. You also might object that this is like clearly insane, like because let's go back up to our picture. So the kind of statement we would want is that this cuspidal vector bundle comes as some extension from the cotangent of the open orbit. But the cotangent of the open orbit in this case just is like an open on just like one of these pieces. And so how is it even going to see, but we're supposed to get a vector bundle out of this. So how is it even going to see the other piece? So that should be an indication to you that the kind of construction that we're going to need here is not one of the functors that we currently know. So let me say something about this. So Jared's about to get upset again because I'm going to,
Well, I have a very basic.
Okay.
There's sheaves on V, and
Yeah.
there's sheaves on TV, or maybe T star V.
Yeah.
There's classes of cuspidals for each, and which ones are under consideration now?
So what we care about in this talk are the coherent ones on TV. T star V. No, tangent stacks will never show up in this talk. Okay, so the point is that constructible sheaves will only show up on the Vogin stack. They're related to D modules on the Vogin stack. There's a functor from filtered D modules to D modules. And if you take the associated graded of the filtered differential algebra, it's like the structure sheaf for the cotangent stack. So that's why when you live on coherent things live on the cotangent stack, the constructible things live on the Vogin stack. Okay, that was a lot of words. Maybe we can clarify this in the Q&A. Okay. What I want to try to do now is we have some constructible statement, and we want to try to get an analogous coherent statement. That's what I'm trying to do. But we need a definition here that will seem unmotivated. So, S is a theta stratum so S living inside the mapping stack from theta to X is a theta stratum if this evaluation map is a closed immersion. And S a union of connected components.
So S is something living inside this mapping stack?
Yeah.
Connected components of the whole mapping stack?
Of the mapping stack.
So it's very tight condition.
Yeah, but we were already considering a connected component of the mapping stack, so maybe it's not so shocking. And a theta stratification is some collection of increasing open substacks. So open substacks of X such that X less than or equal to alpha minus some stratum S alpha is a union of okay, what do I want to write? Of alpha prime less than alpha of X alpha prime. So the point is like this is some stratification, and the pieces, the strata are these like theta strata.
So are X alpha and S alpha leading to first piece?
So yeah, so really maybe I'll write something like image of S alpha under this evaluation map. Right, so S alpha lives in the mapping stack, but there's an evaluation to X.
And is theta still like A1 mod GM?
Theta is always A1 mod GM. That's all we care about anymore. Okay, so the proposition is that we can choose total order on orbits of V respecting closures such that the open orbit is C0, and then the last one is the trivial orbit. So it's like a decreasing ordering. And then this gives, so U sub I will then be the union of J less than I of U sub J. So what we're currently doing is we're constructing some system of open orbits of the Vogel stack, of open substacks of the Vogel stack, where the smallest thing is the open orbit, and then we're like adding on extra like orbits as we go. Okay, and then there exists a co-character. There exists a co-character. Let's just call it nu C. I was going to tell you something about how it's constructed, but maybe I won't. So we'll let X sub I equal the cotangent of TUI. So now I'm considering the quotient of UI by the action of H, so that's why there's a little math BB there. So this, or maybe it should be less than or equal to I, and then S sub I is okay, let's call this nu I then. Is this. So what I'm saying is you can pick some total order on the orbits, and you can construct some co-characters such that you actually get a theta stratification of the cotangent stack. And all right. And so I'll give an example. So if V is this A1 mod GM, then U0 is the open, and U1 is everything. And so then T, the open orbit of the Vogel stack. So there's only two orbits. Yeah. So it's the Steinberg orbit. Yeah. So T, so this X sub 0, this looks like this. So it's just the horizontal piece, and it's missing the thing in the center. And then, of course, X sub 1 is the whole cross. But S sub 1 is like just the vertical stuff. So it's like, yeah. Okay. Okay. So this is a kind of example to keep in mind. Okay. I promise there's a point to all this. but I think it will take a minute to say. The point is we're going to use this stratification to construct some interesting functor. And a motivation is the next theorem. So Halpern-Leissner window categories. So we'll define WC to be F, sheaves F in one of these pieces, such that, oh Lord. Yeah, I'll offer a clarifying statement. Okay, so it's in co of greater than WC, where WC is some specific weight. It's nu C paired with the weight of this thing. Okay, so what is this window category? It's like the category of sheaves F in this TU that are cuspidal on one side for this particular parabolic and not cuspidal on the other side. So like basic on the other side, right? It's greater than WC and less than or equal to WC. So, yeah, okay, fine. And so let me this weight, and this weight is the correct weight. You can just trust me. And so there's a theorem of Halpern-Leissner that I'm hoping will make people happier. So there's this restriction map from WC to co-TUC minus SC. And this is an equivalence. So this window category kind of lives on like the complement of SC inside of this thing.
So can you go back to the example if you're done stating the theorem?
Yeah.
So does that mean in this case that like if you have something on punctured horizontally you drew?
Amazing. So this punctured thing, so the interesting case here is when is x0, right? And so what this is saying is that sheaves on this, in this window category are equivalent to this stack, but this stack ends up being like B of mu2. The classifying?
This stack is not clear what this stack is.
This stack. Sorry. Because it's just one orbit with a group acting on it, so it turns out to be, this is like, in this case, is like B of mu2, thank you. And this is just actually like two things. So what is this thing? Well, there's some debate about signs, but definitely the cuspidal thing should be in here. So that is like the vector bundle on A1 shifted by 1. And then the thing corresponding to the trivial representation should also be in there. So it's very small, and it just contains two things in this case. Okay, fine. So now we can define our functor. So co-T U C I equals co-T U. Okay, so this functor, we're because this is an equivalence now, we're just taking its inverse basically, and the point is that when you take TUC I plus 1 and you get rid of SI plus 1, then that actually is just the smaller stratum, and so then we can define compose for all. What? Yeah, we're iterating now. Yeah, that's my compose. So compose this functor for all CI to get this functor I'll call it exceptional shriek from co t u0 to co.
Is that an exclamation point with an absolute value?
Yeah, this is our temporary notation. Anyone who hates it can talk to Terry. Okay, so.
Sorry, I have one more question. So here we picked total order on the orbits, refining the closure partial order. Does the order matter? It better not, right?
Should not.
Check that it doesn't.
Okay, let's talk later. Okay, so, oh God. So some proposition is that maybe will not shock you is that F is a cuspidal sheaf implies that, okay, okay, no, I need that, sorry. Implies that the pullback is in the window category for all C's. And that's maybe not surprising because this window category was kind of defined to contain cuspidals plus a little bit, right? So, but one corollary is you can do some kind of recursive computation and show that the exceptional extension of the pullback of F is F for F in cusp TV. And well, I mean, and this pullback actually lives on the open orbit now. So this is saying, okay, so now we've exhibited our cuspidal sheaf as some kind of shriek extension. So this feels like maybe a bit of a trick, but the point is this exceptional, on certain sheaves, this exceptional thing satisfies an adjunction relation. And that adjunction relation is very useful because it allows us to reduce certain computations to the open orbit. And well, why might we want to reduce computations to the open orbit? Well, the cotangent stack of a classifying stack is a much easier thing, right, than these full complicated cotangent stacks. And so maybe on the cotangent of a classifying stack, the coherent world is living as close to the constructible world. Like these universes kind of are close to meeting here. A remark, okay, maybe people didn't like that analogy, that's okay. So, is we can define that W has too many pieces. We can define WC prime with like the other window category, like with these conditions. And if we do that and we do this whole procedure, the whole thing works and we get now the star push forward of some sheaf. But in both cases, it's the same sheaf. It's just the pullback to the open orbit. And so this is the cleanness because it's saying that this F is actually the shriek extension and the star extension of its restriction to the open orbit for these exceptional things.
Are these functors exchanged by duality?
Yeah, they should be, yeah. Well, L equals R we kind of already like deduced earlier.
Oh, right, sorry.
Yeah. But this is very useful for proving the generation by cuspidal vector bundles. That is like actually turned out to be a super hard thing. But yeah, so any cuspidal sheaf, you can pull it comes from this open orbit, and on this open orbit, it's much easier to see that these things are generated by cuspidal vector bundles. Okay, I have 15 minutes, doing way better than I thought. So my last thing will be cuspidal vector bundles. That's my third vignette. Okay, so the point is maybe from the kind of stuff we've seen that we know that R cusp equals L cusp. We maybe have proven that, you can imagine that we've proven that these things are generated by cuspidal vector bundles. And it turns out actually the semi-simplicity can also be seen from reducing to this open orbit. But we need to classify what these cuspidal vector bundles look like. And it turns out with all this machinery that I've been blasting at you, it's actually maybe easier than it was a year ago for us. So the situation is as follows. So we have some v in co t star v, and it's a vector bundle. So what we actually have is that this vector bundle is the pullback of some rho along the following map. So this is like an easy thing to prove. I think it goes by the name like equivariant Nakayama. So to classify,
Not assuming these are reducible.
I don't think so. To classify possible of these things, we need to compute weights, as one does.
Sorry, can you scroll a little slower? Thanks.
Yeah. So this is like P composed with sigma in earlier diagrams. And then we have a map like this. And then we have a projection like this. And well, this diagram commutes, and we have rho here, and what we really are trying to compute. So firstly, computing the weights on the new greater than equal to 0 thing by some functoriality is the same as computing weights on like the new equals 0 thing. So we really just need to compute weights on the levy. And so then what we're really trying to do is take rho, pull it back to the cotangent stack, and then pull it to the levy and compute the weights there. But this diagram commutes, so it suffices to compute this way. And because this left vertical map is kind of equivariant with respect to GM actions, actually we get something really nice, which is that the weight of P, these are the same thing as the weights of rho as a representation. We fix the maximal torus of H, and we can consider like the weights. Okay. And then, so some proposition that you can probably prove yourself by now is that this thing is cuspidal if and only if for all weights chi of rho, nu chi is less than nu, and then this funny weight shows up again because it has to. Okay, so we actually have some. So basically, if you have some rho, you want to figure out if it's cuspidal. You just need to figure out what these conditions are, and then you can do it. And sorry. And I'll say Weil combinatorics implies that each chi lies in a convex bounded. I have 10 minutes left, right? Yeah. Polytope that I'll call P-cusp.
Or each chi, which is some relevant gadget, or
Yeah, each chi as above. Okay. And here's a proposition. Assume lambda is dominant and set phi n. So if lambda is dominant, it induces a weight for each positive root. And actually induces a weight for every root. And maybe I don't even need this dominant, but these phi n is roots of weight n. And phi 0 is roots of weight 0. And then here is the formula for P-cusp. This formula is less useful than you might think. So what intarnation is going on here? So what I've written for you, so these bracket 0, comma mu, these are line segments. We're back in linear algebra. So this is the line segment from 0 to our weight, to our root. And then this plus is this Minkowski sum. It's just the set of linear combination, or it's just the set of sums of like things in these line segments. And so we're summing up all these.
So the real character group tensor R is just a real vector space.
Yeah.
Some polytope.
Yeah, at some point we passed to tensoring with R.
Is that a minus sign inside a circle?
That's a minus sign inside a circle. So this plus is the Minkowski sum, and this minus is the Minkowski difference. And so this is like, you take the polytope, this thing on the left is some polytope, and this thing on the right is some other polytope, and this difference is the points x, such that if you translate it by anything in the thing on the right, it's still in the thing on the left. So here is an example that might make Dave happy. What happens in the Steinberg case? In the Steinberg case, there are no roots of weight 0, so it's just this sum on the left. But actually, the roots there are just the simple roots, so it's just the cube given by the simple roots. So this is a nice thing.
Is there a difference between the left-hand thing there and the convex hull of 0 and all of these ends?
Sorry, what? No, it's way bigger than the convex hull because you can sum up all the roots, and that lies. Like it's not a convex combination. Yeah. Okay, and so then some theorem of BMK and leak. So this paper we've completely finished, but we just haven't. There's an early version and we haven't updated it yet. We'll update it soon. So P-cusp has non-empty interior. If and only if open orbit of V corresponds to a discrete parameter. Okay, maybe actually this first part. Okay, whatever. Unwinding all these like reductions. But in this unipotent case, this is saying that this open orbit corresponds to a distinguished unipotent in the classification of Bala-Carter.
You've been in the unipotent case for like how many minutes? Like half an hour?
Yeah.
Okay. So this H lambda is connected reductive, right?
It's a levy.
It's a levy, and
Yeah.
T is a torus in it.
Yeah.
And when you say weights, you mean like you have electric.
Weights of the torus, yeah. It's a levy, so it contains a maximal torus. Right, and so this is kind of surprising because just to say, like, this is saying that a sheaf is, so we've seen that a sheaf is a cuspidal vector bundle. A vector bundle is a cuspidal vector bundle if all its weights lie in this polytope. And the polytope is always non-empty for discrete things. So you might expect that we've got all kinds of cuspidal vector bundles. The problem is the polytope is very, very narrow, and it has very, very few weights. So in practice, there's like some little polytope, but it won't contain any weights, basically, is what happens.
You make me happy by also mentioning like the word basic. Like basic weights, basic points. Like the boundary points.
Yeah. The boundary points of the cuspidal polytope are like the basic weights, and so if your vector bundle has all its weights lying in the boundary in the closure of the polytope, then it is a basic vector bundle. So it corresponds to a basic sheaf. Okay. And then some theorem is that the interior weights of P cusp agree with Lustig's classification. I can't spell. Classif, oh God. And if you haven't seen this classification before, it's like a super crazy thing. Like triangular numbers show up, square numbers show up. So it's kind of like we were a bit excited when we saw this. And finally, I want to leave you with one last example. So if G is SO2n plus 1, G hat will then be SP2n. And phi will be unipotent. Suppose phi is unipotent in discrete series. It turns out that P cusp in this case has at most one interior weight. And it turns out that this will be 1/2 the weight of the dualizing thing of V. Okay, and then it turns out that so let's call this thing chi, and then it turns out that chi is integral if and only if phi has no gaps. If you remember from my third talk. And then in this case, chi restricted to the open orbit is alternating. And intuitively, the reason, okay, you can just do this computation for yourself, it's fun, but like the reason this works is because you have some piece, some big piece, and it doesn't want to be, it kind of makes the weight not integral, and then the only thing that will make it integral again is if you have like the next piece. And so then you kind of go all the way down like this. Anyway, whatever. I mean, that's not going to help you, but you can still do this computation, it's fun.
This only works if n is like a triangular number or something?
Yeah, and it turns out this only works if n is a triangular number because if you think about what you need to have this like no gaps condition, yeah. Okay, so I'm basically done, so I'll stop here.